or present some of the activities of my group at ETH Zurich on the topic of metamaterials. Just to begin with, I'll give a bit of background of what my group does, which initiates really from assessment of structural performance and the development of computational and monitoring approaches for protection of systems that experience injury and deterioration. So as the name of my chair implies, our focus is twofold, is on structural mechanics and monitoring. We deal with aspects from across the line of this chain, from the acquisition of data, which is really accomplished by sensing, to the use of models that are coupled with or are individual from the data, usually taking dynamics and nonlinearity into account, to assess the performance of structural systems, derive useful indicators that are driven from these models, and finally support decisions for the protection of engineering systems and assets. And in this context, we're also dealing with the seismic challenge, let's say. So we have activities along these lines for earthquake applications. One of these has to do with hybrid testing, the mixture of numerical models with physical experiments for testing and understanding of the behavior of complex systems. We now more recently also try to use sensors for monitoring of buildings before and during the event of an earthquake, so that we can fashion warning systems for response reaction. And finally, we also work on vibration mitigation and control, which sort of brings me through this long line to the topic of metamaterials that is only very recent for us. So here, typically, we deal with filtering methods and control methods for semi-active or active control approaches. More recently, we discovered this idea or this concept of using metamaterials for vibration mitigation, let's say, more of the passive approach to begin with. And although it's relatively recent, we have ended up having a group here at ETH that works on the topic, with the first one being Dr. Andrea Colombi, who is an Ambizione Fellow and is a senior scientist in our lab, who is working and leading ideas on the topic. Raquel and Julia, two PhD candidates who are working in collaboration with me and Andrea on development of metamaterials, whose work I will show, and also Vasilis, who's a senior scientist, and Kyriakos and Panos working on this more from the point of view of vibration and engineering and performance, and also dealing with nonlinear metamaterials. So it's really the work of these members that I will try to show today. And I will begin with some numerical investigations, which is where we started from when we got a hold of the idea. We wanted to explore this possibility of forming one-dimensional lattices that can be conceived to be used as protective barriers from a targeted structure when the source is actually an earthquake. And one of our first investigations was a feasibility study, a proposal of a system that can be manufactured that could be used in this configuration. And we tried to also understand what would be the dimensions that are involved to achieve an attenuation of something of the order of a seismic wave. We did this for one-dimensional, but also two-dimensional configurations from the numerical point of view. Looking into the dissipation that is achieved when an earthquake source is entering, let's say, a barrier that is somehow formed. Some of the results showed the challenges that are involved. Our target naturally was to try and create band gaps in this very low range, which is the range that is relevant for seismic applications due to the low frequency content of earthquakes, but also the type of modes that are excited in buildings, which mandate a range that is between 0, 5, or 6 hertz. So in 1D and 2D, we were looking for the designs, and you will find these in these presentations, that would facilitate the construction of a system that would be protective in this respect. And although it is feasible, of course, it creates issues or thoughts about what is the cost that is really adequate for offering such a protection. And some of the further complications that one has to consider is the fact that beside the fact that we can maybe promise such a range, a band gap where the vibration is let's say, reduced. There's also effects of amplification outside this range, which for earthquake type of inputs is something one has to keep in mind, as it's not easy to predict the content of such sources. So we understood that we have to better study the effect, and maybe not just numerically. So one of our first things that we tried to set up was really an experiment, which is basically our sandbox that is at ETH Zürich, which is an experiment that was trying to test the performance of metal surfaces, basically arrays of resonators that are structured in front of a source, so that we can understand the performance in terms of the mitigation and attenuation of waves. The experiment that I'm showing you here is the second round of our experiments, where we try to assess the behavior for surface waves in inhomogeneous media. And I'm saying inhomogeneous because this is a more of a realistic approach as to the type of soils that we actually have when we're discussing protection of buildings and earthquake. Here you see our setup, which includes the 3D laser distance vibrometers. It includes a source, which is a piezoelectric, it's a piezo sensor that creates waves in the form of SWIP or Richter wavelets. And you also, or let me go here, you also see a close-up of the medium, which is an unconsolidated type of granular medium. It's basically silica microparticles. It is characterized by a constant density, but features this kind of power law stiffness profile, which is essentially a representation of an inhomogeneous medium. You see here the array of the resonators. These are 48 sub-wavelength mechanical oscillators, which are deposited or structured in an array at the surface of the granular medium. They are 3D printed, scaled, so that we can actually target a scaled up kind of experiment. So the resonator frequency in the scaling is at about 330 hertz. A value which is chosen after experimentally identifying the frequency content of the shear waves that we have propagating in this medium, and we have tried to see what is the effect of this array in the propagation of the waves. So here you see a result of the experiment, the two-dimensional discrete Fourier transform of the velocity data that is recorded through the 3D laser vibrometer. You see here on the left the reference case, which is the case where the sand is just the pure granular medium, so there's no array of resonators, and this is the propagation of the source wave through the pristine, let's call it, medium when no resonators are actually present. And you can see here that we have a fundamental shear wave, SH1 here, and also a second shear mode that can be clearly discerned. You see that this one is prevailing in the lower range of frequencies, and then later on and with higher speed, with a slightly higher velocity, we have the prevalence of the second mode. Now what happens when you embed the resonators, you see it on the right where we show the dispersion curves with the metal surface. You see that the first mode, which was prevalent in the lower frequencies, interacts with the collective phenomenon, collective resonance behavior of the metal surface, giving this hybridization effect that ends up creating essentially a band gap, and this appears around the frequency of the resonators. The attenuation zone arises at these 330 hertz that I mentioned before. Now, in order to understand if this is really a phenomenon that is owed to the resonators, we also tried the same experiment and measurement for a case where we again have the array of our casings, the 3D printed casings, but without the resonators. So the resonators are removed and only the casing is included. And here you can see that the response resembles more or less the response of the pristine medium, implying that it's really the meta surface that is achieving this kind of a creation of a band gap. Now, we also decided to numerically investigate this propagation throughout an inhomogeneous medium, which is something that is not really done. Usually, a lot of the investigations target a homogeneous type of medium propagation. And to do this, we were trying to calibrate some sort of parameters for the medium, the power law basically profile parameters, which was done through an iterative process by solving an eigenvalue problem that results by the depth-dependent Helmholtz equation. And so by doing this, we're able to more or less calibrate or figure out what is the power law profile that would best agree with our experimental data. And so you see here the analytical dispersion curve, which is contrasted to the experiment, well, and using these now derived velocity profiles, we try to do a numerical simulation. This is done in COMSOL using unit cells with the resonator and without embedment of the resonator and appropriate boundary conditions, absorbing and block Floquet boundary conditions. And you see here the numerical reconstruction, which is able to verify what we observe actually in the experiment. And we did that because we wanted the certainty of being able to what it is that we observe. So here I'm going to show you one more result purely from the experiment. I'm going to play a video where you see the propagation of these waves on the surface by plotting the laser vibrometer response, and having filtered this in the attenuation zone from 330 to 500 hertz, which is our band gap. On the left, you see the medium without any metasurface. On the right is the medium with the metasurface. And you can see that when the waves are traveling within the metasurface, and when they impinge the mechanical oscillators, the waves are scattered and attenuated. And there is also an explanation here which we offer for what happens exactly in the first, at the front, where you have the wave hitting the resonator line. And there you see the comparison between the signals in the case without case one and the case with the metasurface. Which basically reveals that there is the frequency content of the reflected signal really falls inside the frequency range of the attenuation zone and the resonator, which implies that the wave energy is backscattered by these oscillators, which is what we were trying to do in the first place. Now, the further complication here is really what happens also along or across the depth of the medium, and that's where our numerical simulation and updated model helped. Raquel actually performed this simulation using SpecFem 3D, where you can see also in this last plot what happens in the volume along the depth of the medium. And here, the reason why I mentioned this is to demonstrate the shear wave propagation with and without the metasurface. And where we see that part of the shear waves that is not reflected by the resonators actually travels under the resonators. It's significantly attenuated, but it has to be understood that in these inhomogeneous soils, you have this effect where the wave actually travels under the resonator zone and could actually be reflected, even though with the less power after the barrier. Now, what I would additionally like to show is another solution we're looking at, which is not of the barrier type this time, but rather of the in terms of meta foundation, let's say, which is of course something that is quite heavily recently looked at in literature and by colleagues. Some disadvantages we could see is that often it means large dimensions. It's not always granted that there is a possibility to bear the vertical loads. And the lateral stiffness could also not be so sufficient. And what we proposed to experiment with, just because we wanted to also check this from the point of view of feasibility, was the possibility of using existing solutions for base isolation, basically commercial rubber bearings, specifically the ones that are produced here in Switzerland is what we used specifications from in Mageba. One of the providers. So we tried to see if we can do alternating layers of these rubber bearings and concrete slabs to create a meta foundation for realistic structures. So here you see one of the structures we actually could simulate that is here in Zurich, a building which we placed on top of this foundation. And so in this case, Julia again performed a SpecFem simulation, which is more of a linear analysis software, but as a first stage performed the simulation to see what kind of modes are excited by use of this foundation and what is otherwise the excited response of the building. So we used this kind of layered logic. And here I show you the analysis framework, which consists in an input source being inputted into the building, usually chosen at around the first resonant frequency, as would also be the seismic design sort of approach. We did this for both the slab foundation and the layered foundation, and tried to compare the outcomes in terms of the time response and the frequency response of these signals. And here you see a close-up, or rather an explanation of how the input source is being applied, which is a Richter wavelet centered around the first mode of the building, here at about 1.5 hertz. We give the source as an input with components in both the X and Y direction. And then we do the comparison of the drift of the building without and with the layered foundation. Here you see obviously the effect of the mitigation and the amplitude reduction, but what is also interesting for us to note is the type of motion. So actually, let me show you here the videos, the visualization of the response of the systems with the layered foundation and without. You see here that the vibration is actually mainly localized in the foundation. So this was a behavior that Julia wanted to explore a step further. And to do this, we try to check the main modes that are excited by the type of source that we're applying. And so here you see the bending mode of the building that is primarily excited at about 1.50 hertz. And additionally, a second peak in the spectrum that corresponds actually to the foundation mode. And this is where a lot of the energy dissipation comes from. So a large part of the energy is trapped in the foundation, which is this design that includes the lid rubber bearings. Here is also a visualization of the mode or of the foundation, which a very good thing here is that this mode is of course separate to the structure. It's really a characteristic of the system, and it is a tailorable mode in the sense that we can, by design, configure what this is. Maybe as a last statement, I should explain that while this previous analysis started to see the wave propagation, so it was done in a software that is primarily linear, we also did the proper structural, let's say, analysis using the base excitation to the system of foundation and building. Here we are using the nonlinear constitutive relationship that we know describes this kind of a damper, more or less bilinear. And again, we tried over different time histories. I'm just showing you one of the possible waveforms here. We use design earthquakes on the basis of the spectrum here in Swiss sites. And we show that the comparison between traditional base isolation and this layered type of meta foundation, where a significant decrease is noted both in the response of the structure, but also in the response in the displacement of the isolation or the foundation system. And maybe as a closure, because I know we don't have much time, I leave you with this idea that we're exploring on nonlinear metamaterial concepts with Vasilis and Kyriakos. So here, we wanted to move away from the currently used linear resonator designs. We wanted to try nonlinear candidates that can again be thought of as a unit cell design that can be recombined to form a chain. And there's many alternatives that exist and have been proposed in the literature, and we will be looking more into these two options, the meta-impactor and a concept that exploits geometric nonlinearity. So for the meta-impactor, we're talking about basically, again, a lattice system, but now a lattice of multiple impact dampers, mass and mass systems, but the inner mass is laterally unconstrained and free to impact on the sides of the system. And in the end, you can think of this more of a sphere inside a container type of impactor. The impact phenomena create a highly nonlinear and non-smooth sort of resulting dynamics, and this is interesting for us for the point of view of analysis, understanding in which way we can use it to maximize the dissipation for the overall structural vibration. To study this response, we try to do this using the equations of the system to begin with, just with an analytical assessment, using the conservation of momentum equation and the definition of the coefficient of restitution. This gives us a relationship between the prior and post-impact velocities, which we use to understand the energy dissipation at each impact. specifically, we try to formulate this by using a metric of energy dissipation. This metric is here the ratio between the energy absorption resulting from all impacts, which you see over here, over the total input energy to the system. And by doing this and examining different types of possible designs, meaning mass, inner mass to outer mass ratios, or then also the ratio of the resonator with respect to the mass of the system we wish to have controlled, we understand how this kind of energy absorption can work. What is interesting from our point of view is to go as low as feasible, which is really the more problematic area. As you see here, ideally we would like to have energy absorption that is more or less uniform in a graph, but when you go to low masses, which makes the system more easy to realize, obviously you get a behavior that is not necessarily optimal, and does not also depend, as we saw here, with so strongly on the number of resonators. So we're trying to explore now this gray line as to how to bring this ratio down, but still try to have a significant energy absorption. And to do this, we're also looking into other alternative designs. So the second one, and the one I'm closing with, is the geometrically nonlinear lattice, which exploits this sort of, let me show it here, geometric configuration, a triangular arch, which can be calculated analytically. We know it is a geometric type of nonlinearity, and we exploit it in order to create a new type of unit cell that is nonlinear in nature. The good thing is it can be approximated analytically, which we try to exploit for understanding the dispersion relationship using an infinite lattice and using Bloch theory, exploiting the Bloch periodicity, and we use the harmonic balance method to try to understand the resulting dynamics. And so you see here that indeed we can create a band gap, and in fact this band gap depends not only on the frequency and wave number, but also on the relative oscillation amplitude, which is something that is an artificial artifact, something that's created from our harmonic balance type of analysis, but it gives us confidence that we can indeed create relatively large band gaps with this kind of a concept. To conclude, as I know I have exceeded my time, we're looking into these potential, as you saw, from different aspects for using metamaterials for structural vibration mitigation or absorption. We have looked into barriers, which has revealed some limitations, but looks highly, at least for seismic applications, but looks very promising or more feasible for shielding structures or machinery from man-made vibrations, maybe railway-induced vibrations. We looked into meta foundations as something that can indeed be a replacement to existing type of base isolation systems. And we tried to experiment with a design that could already be materialized because it's using just commercial bearings, essentially. And we're also trying to look into the use of nonlinearities for extending our reach. This concludes my summary, and we, of course, welcome any questions and comments from colleagues.